Today I would like to continue with the term crystals. If you remember in the first video, I told you that actually mineral is a natural crystal, so a crystal that is formed by nature, which means without human intention. However, the title of today's video is not by accident. This word crystal is in between minerals and synthetics. It is because both minerals and at least some synthetic compounds are crystals. For comparison, I will remind you this guy. So this is a compact mass of halcanthite, which is a natural copper sulfate 6 pentahydrate. Do you see crystals here? Believe me or not, but these blue masses are being made of crystals, which are actually natural crystals. So minerals, actually it's one mineral, single mineral, known as halcanthite. So this is a natural analog of this copper sulfate 6 pentahydrate. And for comparison, at the bottom of this cup, again, you see these blue dots. As you can see, the color is quite similar. These are actually remnants of my trial of producing a synthetic compound, which is a copper 2 sulfate 6 pentahydrate. Both of these objects I showed you are crystals. The first one is a mineral, the second one is a synthetic. Okay, but what is this crystal? So crystal is a term that you will find both in mineralogy and in chemistry, but it's more like a physical-chemical term. And you can look at the crystal that it bears a group of atoms. So if you take a group of atoms and you set them in a very specific way in the space, then it turns out that these atoms might be set in a very chaotic way. So if you take a larger look at this group of atoms, you will not see any similarities, any motifs that repeat. In this case, you probably see an amorphous substance. However, if you see that some types of sets of atoms, some groups of atoms are being set in a similar fashion, then you probably look at the crystal. When you look at the space of this, or in this internal part of the crystal where the atoms exist, then there's a thing that is called a unit cell. And this, you can look at this unit cell as, for instance, a cube, maybe a rhombic shape. And inside this cube, for instance, you have enough sodium and chlorine atoms to build a whole crystal, for instance, of sodium chloride. If this is a mineral, then it would be called halite. How is it being done? Very simply. If this is, for instance, a shape of our unit cell, then you copy-paste it in one direction, so the second one, third one, fourth one, etc. Then the second direction, which would be Y, and third, which would be Z, as long as you reach faces. Because if you look at a crystal in a macroscopic term, or if you use a binocular or a microscope, a polarization microscope, you can also see crystals. Also, if you go to a scanning electron microscope, but we are looking at the outside part of the crystal, so we are looking at crystal faces. This science is called crystallography, and it is usually used in mineralogy and sometimes in chemistry too. But believe me or not, the way the faces, the crystal faces, the faces that close the crystal, the way they're being set against each other, it's not by accident, not by chance. They repeat geometry of the interior of the crystal. If we talk about geometry of the interior of the crystal, then we are actually talking about crystal structure. And if crystal structure, then it's called crystal chemistry or crystallochemistry. And again, crystal chemistry both denotes natural crystals, so minerals, mineralogy, and synthetic compounds that are being either made by a chemician in the laboratory, or for instance, internal of some kind of industrial process. This is crystal chemistry. Okay, but what governs shapes of crystals? Both if you look at the outer part and inner part. Of course, there would be elements of symmetry. So symmetry. What kind of elements of symmetry we have? So the first, basically the most simple one, is center of symmetry. It is being usually written as number 1 with a bar above it. So this is sometimes the bar is being written before 1, so this is -1. Sometimes it's also being called C for center of symmetry. Then we have a quite large group of symmetry axes. What kind of axis do we have? So the first one is quite strange. Let's say this axis goes parallel to my finger and points to, what is it? Okay, Titan. And if we place a number 1 without this bar above, then we are talking about something called identity. Other name for this element of symmetry is an axis with a multiplicity of 1. And how it operates. So if this is an atom, then we rotate it against this axis back to its place. So we rotate it by 360 degrees. So basically we do nothing. This is why it's called identity. However, it is being understood as one of the elements of symmetry and one of types of axis of symmetry. However, if you take another type of axis with a multiplicity of 2, so if you see number 2 in the kind of description of crystals, then what happens? If we divide 360 by 2, then we got 180 degrees. So you rotate, but for 180 degrees. And what we get here in this point, more think about, is a copy of a crystal. Okay, so we get a copy of crystal. This is what the axis with multiplicity of 2 does to a crystal, or does to an atom, or to a group of atoms, for instance. Then we have threefold axis. So we have 3 rotations, each by 120 degrees. Then we have a fourfold axis, which brings 4 rotations by 90 degrees. And finally, the most complex one, the sixfold axis, which brings 6 rotations by 60 degrees. More or less, each of those axes are typical for a very large group of types of sets of elements. And these groups of sets of elements, the most basic one is called crystal system. So, for instance, we have a cubic crystal system, which is very, very high, the highest symmetry. So we have a large number of elements of symmetry. And what is being usually done in crystallography classes, both in mineralogy and in chemistry, is, for instance, we take a cube, so a model of a cube, and we try to write on a paper the way the faces are being set in this crystal. And from these writings, we can guess which kind of elements exist. So which kind of elements are needed to obtain this set of either faces or set of atoms. In this cubic system, we have plenty of symmetry elements, but the one which is important is a threefold axis. However, not alone. So we need, for instance, a threefold axis and a group of other axes, and also a representative of the third group, which is actually as long as we are outside the crystal, a single element group, and this third, the last type of symmetry elements is simply a plane. So if this is a plane, it goes now hits my eye, for instance. Yeah, this is a plane, and we have an atom. Then the plane simply acts as a mirror. So the atom is being copied to the other side of the plane. So the plane acts as a mirror. Things are simple, more or less simple, if we end with the outer part of the crystal. Okay, if you have just a single threefold axis, not 4 ones. as in the cubic system, then we are in a so-called trigonal system. If we have a single or any actually any six-fold axis, we have a hexagonal crystal system. If we have a single four-fold axis, we have tetragonal one, and there are also other types of crystal systems, but I wouldn't like to talk much about this now. If we enter the interior of the crystal, so if we are trying to describe the structure of the crystal, so basically if we look at the atoms and the way they are being set, things get more complex because I told you that atom is actually the crystal is actually being done by a constant copying of this unit cell, this shape, this motif in the structure. And this copying is actually, in terms of geometry, called translation. This translation exactly invokes two different types of symmetry elements. First type are also axes, but they are screw axes. So what they do is, if this is a screw axis with a multiplicity of two, so this is a twofold axis, then the simple one makes something like this. So there's a rotation, by 180 degrees. However, then is the place for this screw. So what is the screw? The screw part of this operation of this axis is simply a translation. So this atom is being moved parallelly in a parallel mode to the way the axis goes. So like this, yeah. Of course, this length of which this atom is being translated is not again by chance, and it is a 1 second or a half of a very specific length, which is characteristic to the very exact type of a crystal. Why half? If you go to literature and you see number 2 with the lower case and there 1, so 2 1, then this 1 means that this axis has a screw in which the length of the translation is 1 per 2, so lowercase divided by the multiplicity, and then multiplied by a very specific length, which is characteristic of a very crystal. For instance, a crystal of copper sulfide pentahydride. So with the twofold axis, it's simple. If you go to threefold axis, we actually have two types of threefold screw axis. So we have 3 with the lowercase 1. So in this case, we have 3 rotations. However, after each rotation, this copy of an atom is being moved by 1/3. So yeah, so 3 1, we divide 1 in the lowercase by 3, which is the multiplicity of the axis. But we also have a 3 2, so 3 with the lowercase 2, and in this case, after each of the rotations, the trace of the atom is being moved by 2 per 3. So lowercase 2 divided by, again, the multiplicity. Believe me, if we get to the sixfold axis, things get even more complex. I wouldn't like to talk much more about this details of this axis, but one more thing is important. I told you that there are 2 additional groups of elements of symmetry if we describe the interior of the crystals. So the first one were screw axes, and the second one, as you probably would guess, is a new type of planes, and exactly the planes are slide planes. What basically they do is the same as with the axis. The difference is this first operation. It is not rotation, it is a mirror. So the atom is being moved to the other side of the mirror plane, but then again it's being moved, and in this case we have different directions depending on the type of axis. So if you see, okay, so no axis planes, sorry. So if you see a small letter M, this is how we describe a simple plane, so a mirror plane. This is why M. Any other small letter like A, B, C, D, N, and which is being actually known for not a very long time, E, these are exactly types of slide planes. Quite interesting is the N type. because after the mirror operation, we have not one but two translations of this atom. So this is things here are getting quite complex. It is quite important to say that there are more or less finite groups of this elements of symmetry. If we describe the outside of the crystal, so we are looking at the faces of the crystal, we use so-called point groups. Sometimes in mineralogy, especially, they are called classes. However, if we are describing the interior, and you probably get this idea that the number of these second types of groups of elements of symmetry are much larger. Actually, there are 230, or was, because it kind of grows. Then we are talking not about point groups, but about space groups. So we are talking about a space. So an example of a space group is, for instance, which is quite common space group, is for instance a C, a large C, 2 / M. What is this first letter? Is basically it's a Bravais type of unit cell, and it tells you a quite simple thing. If you look at the unit cell, so this motif in the space, which contains enough information inside to constitute the whole crystals by copying this motif, this unit cell. So if the this first large letter tells you about where are the atoms located against, for instance, this cube. Okay, so if you see large P, which is for primitive, it means that the atoms in this unit cell, which describes this kind of a set of atoms in this kind of a crystal, then it means that the atoms are only sitting in the edges. So this is a primitive type. Then we have a type with a large letter Y, and this means that the atoms are not only in the edges. For instance, in a cube, if the unit cell has a shape of a cube, of course. So you have the crystals only in the edges. So you begin from this primitive type. But in addition, there's one crystal exactly in the center of this unit cell, in this case of this cube. This is Y. Then you have, for instance, face-centered types of Bravais types of unit cells. So you have letter A. This is a situation where you have, again, for instance, this cube. You have atoms in the edges. So again, you start with this primitive type. But then, if you look at the faces of this unit cell in the shape of a cube, for instance, if you look at the faces that are being set along direction X, so if this is a cube, this will be this face and this face. Yeah. So then the atoms are also in the very centers of the faces that go along X. So here and here. Yeah. So in the other words, if you have a primitive type of a cell which shape is in a cube, you just have 4 atoms in the edges, because not 4 but by 8, of course, because the cube has 8 edges. If you go to a face-centered type of a Bravais type of a unit cell, you have 2 more atoms exactly in the centers of the faces that go along direction X. B is, of course, when we are talking about faces going alongside Y, and Z, the faces on the top and the bottom of this unit cell in the shape of the cube. Shapes of unit cells, there are plenty of shapes, and as I told you, the number of the groups, especially actually only the space groups, is quite large, at least 230, but likely more. And in the end, I would like to tell you a little bit more, very little, about some discrepancies from this theory of what is actually a crystal. I told you that to make a crystal, we need this motif, which is called the unit cell. It bears all the atoms and a very specific set of the atoms, so the way they're being set against each other, to build the whole crystal and close it with faces. The faces of the crystal actually repeat especially the planes that are in the crystal, but this is an asterisk is needed here. Of course, there are no planes in the crystal. This is actually our imagination that there are some planes in the structure, but of course nobody puts anything like a plane there. It's quite important to actually remember it, but it's quite obvious on the other hand. Well, I told you that this copying of this unit cell takes place in each direction, but this not necessarily need to be true if we switch to quasi-crystals. Quasi-crystals is a kind of strange, a very interesting type of solid, which is not a crystal, but some kind of a crystal, we might say. What is it? Okay, so these groups of elements of symmetry that govern sets of either faces, if you're talking about point groups, or atoms, if you're talking about space groups. These sets are more or less finite, and this, but there are some sets that are sometimes called forbidden symmetries. Forbidden or not, mathematicians a very long time ago could make some shapes where, for instance, a five-fold axis would be needed to obtain such a shape. Other ones did some objects with 10-fold axis needed. The other ones with 11-fold one. Within this space groups, at least the space groups that describe crystals, sensu stricto, there are no 5-fold axis, 10-fold axis, or 11-fold axis. However, again, quite a long time ago, a chemician was able to mix some portions of metals like aluminum, iron, nickel, or copper, and he was actually able to make a crystal that actually was kind of strange because it contained some five-fold motifs inside. So its symmetry was governed especially by a 5-fold axis. However, this was not a crystal. This was exactly a quasi-crystal. Some years ago, not very long time ago, a brilliant Italian mineralogist, Luca Bindi, was analyzing quite an interesting meteorite known as Katurka meteorite. It comes from Russia. And guess what? He found at least 2 natural quasicrystals, minerals. One is called icosiodrite, the other one is called dicagonite. Especially the name of this latter tells you about dica, which is 10, gonite, gonio, which is angle. Exactly, there in the structure of this. If you look at the structure of these crystals, we see some elements with 10 angles. This structure contains a 10-fold axis. So it turns out that quasicrystals are not only being synthesized, but they are also some minerals are also quasicrystals. How can we look at this quasicrystal? It's quite difficult even for people that normally work with crystals. But I can only say one thing. Some people say that to describe the quasicrystals in the way we are describing crystals is to use a next thing, which is time. So not only we need to go to a 4th dimension. This is why the quasicrystals are sometimes called time crystals. And with this kind of curious information, I am ending this video. Thank you for watching. I invite you to contact me or watch another videos. And by the way, I wish you much better 2021. Cheers.